Hi, welcome to our first video for 6.2 Recursive Procedures. So in the last section, we learned explicit formulas. Okay, and explicit formulas basically have this form. They'll be written as Tn equals, and then usually we have maybe like something times n, maybe it's squared. But this is an explicit formula because we can calculate any term in the sequence. We just need to know the term number, which is n. So if we know the term number, we can plug that in, and then we can get the value of the term t of n. So for example, if I wanted to know the third term, that means n is equal to 3. So t subscript 3 equals 2 times 3 squared, which is 2 times 9, which is 18. So the third term in the sequence would be 18. So I could use this explicit formula to develop uh, as many terms as I want for this sequence. So this is basically what we did for 6.1. So for 6.2, it's a little bit different. We're looking at recursive procedures. So sometimes, and when I say sometimes, I mean like maybe in the context of computer science or biology, it might be helpful to determine a term in the sequence by using the previous term. Okay, so instead of entering the term position, like the third term, and calculating it, for a recursive procedure, you need to know the previous term. And what we do is we use a pattern and the previous term to get the next term. So here's an example of a recursive procedure. So let's look at this diagram right here. So this is the first diagram, and then it grows to this one, and then it changes again to this one. Okay. So if you think of this as like term 1, 2, and 3, there's a pattern here. Okay. You can pause the video, see if you can draw the next two terms for this pattern. So I'm going to go ahead. I'm going to do that right now. I'm just going to move this out of the way. So to draw the next term, I kind of want to copy this out. So I'm going to cheat a little bit and use the copy method on the iPad here. So I'm going to copy this out right here, and I'll paste it over here. So if I had to do the next diagram, notice it's always something's always being added. So from this one to this one, a square was added. So this would have been added on the right. And then in this diagram here, we have the previous two squares, and then we added a bigger square on top of it. So if I had to complete this pattern, to me, it looks like I'm adding another square, and its side length has to be as long as the previous terms. This is the previous, so like this length and that length. So it's going to create a large square right here. So I'm going to go ahead and I'm going to add that in. I'll add it in red so you can see what's being added, and it's a square, so they're equal side lengths. Okay. All right, now we're going to copy this, paste that over here, and I'm going to create the next term here using blue. So I need to generate another square. The new square has to have a side length that's equal to this red one and the previous one. So it has to be that long. So I'm going to draw it over here. So maybe you get the pattern now. You can see that for every new diagram, we're adding another square that's as long as the previous two terms. So if I were to draw the next pattern, it would be way out here, and it would be a square with that as a side length, which is as long as these two. Okay, so it says express the side length of each square in the form of a sequence. So to write this as a sequence, if this is my first term, let's say that has a side length of 1. Okay, so that's the first term. Okay. Now the second diagram, we added a square right here, also has a side length of 1. Then the third diagram, when we added this square has a side length of 2. So it's the previous square and the one before that. So this is a side length of 2. And the third term, this new square, is, I can tell it's, this is 1 here, and this length here is 2, so that adds up to 3. And then in the fourth term, this big blue square, I know that this here is 3. That was the previous length that we used. Plus we have another 2 there. So a total of 5. Okay, so looking at this sequence of numbers, can you try to find a pattern here and see if you can predict the next 3 terms in the list? So if you want to pause the video, that's totally fine. Go ahead and see if you can predict the next 3 terms in the list. Okay, so if you notice, there is a special pattern here. Every time we draw a new square, the square is as long as the previous 2 terms. Okay, so this square, its side length is as wide as the previous 2 side lengths right there. This term here, its side length, this length right here, is as long as this side length from the previous square plus the one before that. Okay, and then this blue one here, how big is that square? Well, it's as big as the previous square in red plus the side length just before that. So the new square is always, its side length is always as long as the previous 2 side lengths. So what does that mean about the list? Well, if this represents the side lengths, to get the next side length, I just need to add those 2 together. So we would get 8, and then the next one would be 5 plus 8, 13, and then 13 and 8, 21. So do you see how to get the next term? We're always adding the previous 2 together. Okay, so just so you're aware of this, that one was 5 plus 3. 13 is because we did 5 plus 8. And 21 is because we did 13 and 8. Okay, so it says this sequence is named after an Italian mathematician. So his name is Leonardo, like any good Italian man, and his last name is Fibonacci. So it doesn't get any more Italian than that. So he discovered this pattern, and this famous pattern shows up, in nature and flowers and shells and whatnot. It's actually kind of cool because there is the first home that was ever 3D printed in Canada. My brother actually works for that company as part of that team. They printed, it's called a Fibonacci house. So it's based off of this design kind of up here. So the walls grow out as a spiral. And so it looks something like this as it grows. So I'll touch a video showing that house if you're interested in looking at it, but it's kind of cool. So yeah, the Fibonacci sequence shows up in many places, sometimes planned and sometimes unplanned. So whenever a pattern uses previous terms to determine the next term, okay, so whenever we're trying to figure out a term in a sequence and we need to use the previous terms, we're doing a recursive process or a recursion. Okay, so it's called a recursion. So for the Fibonacci sequence, if I wanted to try to come up with any term in the sequence, I need to take the previous term. So if I'm looking for the nth term, I need the term just before that. So to get the term just before that, I'm going to write it as n minus 1. This means the previous term. Okay, so it's a term just before the one that I'm looking for. And if you remember, because we always added the previous two to get the next, so n minus 1 is the previous term, and then I need the term just before that as well. So this would be the nth term minus 2. So these are all subscripts. Let me make sure that looks clear. So Tn minus 2. So this is a subscript. It lets me know the term. So this one would be the second previous term. Okay, so if I was looking, let's say, for the 10th term, okay, so T10, that's the 10th term. That means n is 10. I'll write that in brackets, n is 10. Then in my formula, I just got to put 10 in for n, so it's going to look like T, 10 minus 1, plus T, 10 minus 2. So, excuse me, so 10 minus 1, that's 9, so that means the 9th term. 10 minus 2 is 8, so that means the 8th term. So you can see how that works. To get the 10th term, we need the 9th term and the 8th term. So we just add them together. So that is an example of a recursion formula. So this one here is for the Fibonacci sequence. Okay, so let's look at our first example. I'm going to zoom in just a bit here. So it says, write the terms of a sequence given the recursion formula. Write the first 4 terms of each sequence. So you might have been thinking this, when you're given a recursion formula, how are you going to find the terms? Well, if you're looking for a term, you need the previous term. So these questions always need to start you off with a term that you can use. Okay, so let's go with part A. So we want to write out the first 4 terms. So T1 is equal to 3. If I'm looking for the second term, this is when n equals 2. Okay, so let me write out the formula first. The recursion formula is Tn equals Tn minus 1 minus 2. So if I had to read this formula out, I would say the nth term is equal to the previous term, n minus 1, and then minus 2. So if I want the second term, take the first term. So if I want the second, take the first term and then subtract 2. That's all I'd have to do. So the second term is when n is 2. I'm just going to spell this out. You don't always need to write this out like this. You can just go ahead and do the math. So it's going to be T1 minus 2. So we said the first term was 3, so we'd have 3 minus 2, which is 1. So we found T2 equal to 1. So we found the first term, second term. If I want to get the third term, this is when n is 3. So it's going to be the second term minus 2. The second term is 1, because I already know it right here. That's why I put in for 1. 1 minus 2 is negative 1. So the third term is now negative 1. Okay, the fourth term, T4 is going to be T3, which is the 4 minus 1 minus 2. So T3 minus 2. The third term is negative 1. So negative 1 minus 2, it's negative 3. So therefore, if I were to write this out, I would say 3, 1, negative 1, minus 3. And that makes sense. I could see in this formula right up here, to find any term, take the previous one and subtract 2. So 3 minus 2 is 1, minus 2 again is negative 1, minus another 2, negative 3. My next pattern would be negative 5 and negative 7. So even once you do a couple, it's really easy to finish this off. Okay, and I'm all out of space, so I'm going to shrink this, and we'll do the next one. Okay, if you understand the pattern, you can go ahead and just answer the question. You don't need to write everything out. So for part B, I'm going to write out the recursion formula. Okay, so we already found the first term, so that's right here. It's given to us. The second term, I'm going to substitute an 2 for n. So that's f of 1. F of 1 is negative a half, so negative a half plus 3 over 2. That's actually 2 over 2, which is equal to 1. So f of 2 is 1. Okay, let's find f of 3. So understanding the pattern, f of 3 means I'm going to have to do f of 2 plus 3 over 2. I can just go ahead and write that. F of 2 is the previous term, plus 3 over 2. F of 2 was 1. So get a common denominator, 2 over 2 plus 3 over 2, 5 over 2. And then the fourth term, that's going to be equal to the third term, plus 3 over 2. So we would have 5 over 2 plus 3 over 2. And that's 8 over 2, which is 4. So therefore, for part B, my sequence would go negative a half, 1, and then 2 and a half, and then 4. You can see that I'm going up by 1 and a half each time, right? That's exactly what this says. It says take the previous term and add 1 and a half. That's how the recursion formulas work. Okay, that's it for this first example. I'll see you guys in the next video.